Hey everyone, and welcome. So, when we look at a set of data, most of us jump straight to the average, right? But what if I told you that the shape of the data tells a way more interesting story? Today, we're going to dive into two really cool concepts that help us understand that shape: skewness and kurtosis. Let's jump right in.
So what do I even mean by the shape of data? Well, think of it this way. It's all about how the different data points are spread out. Are they all clustered together neatly in the middle? Or are they kind of lopsided? Are there a bunch of wild, extreme values that pop up out of nowhere? By the end of this, you'll have the tools to answer exactly that.
Okay, so to understand all the different interesting shapes data can take, we first need a starting point. You know, a perfect model to compare everything against. And in the world of statistics, our gold standard is that famous bell curve.
And there it is, the normal distribution. Just look at it. It's perfectly balanced. The highest point, the peak, is smack dab in the middle, and it slopes down perfectly and evenly on both sides. This is our ideal, our North Star for understanding every other shape we're going to see.
Now, the key ingredient that makes that bell curve so perfect is symmetry. Just like it says here, it's a perfect mirror image on either side of the center. If you drew a line right down the middle and folded it in half, the two sides would match up exactly. But here's the thing, real-world data is almost never this perfect.
So what happens when the data isn't so perfectly balanced? What if it leans? Well, that's where our first big concept comes into play. It's called skewness. And it's basically a way to measure how much our data is leaning to one side or the other.
The official term here is that skewness is a measure of asymmetry. But honestly, the easiest way to think about it is as a single number that tells us if our data has a long tail stretching out to one side. And more importantly, it tells us which direction that tail is pointing.
Okay, and this slide breaks down the two types of skew perfectly. If you see that long tail of data points stretching out to the right, we call that a positive skew. A classic example is income. Most people earn a similar amount, but then you have a few billionaires creating that long tail to the right, which pulls the average way up. On the flip side, if the tail stretches out to the left, it's a negative skew. The most important thing to remember here, the direction of the tail tells you the whole story. Just follow the tail.
All right, so skewness is all about the data leaning left or right. But what about the ends of the data? What about those really extreme values? You know, the outliers. This brings us to our second really big idea for today, kurtosis. Kurtosis is all about the tails. It tells us how heavy or light the tails are. So a distribution with fat tails, like you might see with daily stock market returns, means you're much more likely to see those huge, surprising swings, those extreme outliers. On the other hand, thin tails mean those kinds of surprises are a lot rarer.
And how do we measure this? Well, we always compare it back to our perfect benchmark, that normal distribution. The actual measurement of how different a distribution's tails are from that normal one is called excess kurtosis. It's basically our yardstick for measuring the potential for outliers.
And this whole idea kind of breaks down into three main flavors. First up, you've got a leptokurtic distribution. This means it has positive excess kurtosis, which is just a fancy way of saying it has fatter tails and more potential for crazy outliers than normal. Next is Mesokurtic. That's our perfect benchmark, the bell curve, with zero excess kurtosis. And finally, you have Platykurtic, which has negative excess kurtosis, meaning it has thinner tails and a lot fewer surprises.
So we have a way to measure the center, the spread, the lean, and the tails. And you might be thinking these are all just separate ideas, but they're not. In mathematics, they are all beautifully and elegantly connected in something known as the four moments of a distribution.
And here's how it all fits together, like a perfect puzzle. The first moment gives us the mean, the center of our data. The second moment gives us the variance, which is just the spread. The third moment, well, that's skewness, the lean or asymmetry we just talked about. And that fourth moment is kurtosis, the tailedness. Together, these four moments give us a complete mathematical description of our data's shape. Pretty cool, right?
So at this point, you're probably asking, okay, this is interesting, but why does it actually matter? And the answer is pretty simple.
Because the average number is only a tiny part of the picture.
Because the shape is what reveals the story behind the numbers. A positively skewed income distribution tells a powerful story about wealth inequality. A fat-tailed distribution for stock returns tells a really critical story about market risk and the very real possibility of a crash. The shape gives context and meaning to what would otherwise just be a simple average.
So I'll leave you with this. The next time you see a chart or a graph, look beyond the average. Really look at its shape. Is it leaning? Does it have fat tails or thin tails? What's the real story that the numbers are trying to tell you?